right. Hello, everybody, and welcome to the stream. Hope everybody's doing well tonight. Tonight we are going to do something a little bit different than what we've been working on the last several streams, just to kind of change the pace a little bit. So before we jump into that, I would like to take just a quick second to thank the supporters of the channel, starting with the partners who are the highest tier of subscription over on Patreon and YouTube memberships. They are Arslia, Gerbullies Inc., and Patrick Kuhlman. I'd also like to thank all the other fine people on the screen listed under the supporters section. They are the other tiers of support over on Patreon and YouTube, as well as Twitch subscriptions. So thank you guys very much for your support. It is greatly appreciated. And of course, I feel like it goes without saying, but I'll say it anyways. I want to thank each and every one of you who are chatting here and interacting with me here on Twitch, or whether you're interacting with me over on YouTube. Of course, without you guys, this project would not be possible. So thank you all very much for being here, and I appreciate you all. So, all right. So tonight, I figured we would probably change the pace a little bit, because we've been working on UI stuff for a little bit, and it'd be nice to kind of get some other stuff in. So that's kind of what I have on the roster for tonight. And we're going to actually tackle, I think, 3 things tonight. And the first thing is going to be, we're going to tackle a long-standing issue with the build process, where there has been sort of a disconnect between Windows builds and builds on Linux and Mac. So we're going to handle something there real quick and go through that explanation. And then we're going to address a serious performance issue in the engine and get a big boost in performance there. We'll go ahead and hit that next. And then last but not least, I've kind of teased it a couple of times. We have an audio feature branch that I would like to go through with you guys and hopefully get that in tonight. So that is kind of the plan for tonight. So we'll see how far we get. Hopefully we can get through everything. All right. So, with all that said, I just realized I didn't post my notifications, so let me do that. So with all that said, the first thing that we're going to take a look at, actually, is the symbols issue that I alluded to before. So, on Windows, with the way that Windows works sort of by default, / the Visual Studio compiler, essentially, when you're compiling a DLL, a shared library, whenever you compile that, by default, symbols are not exported. And so we have to go through this sort of process of putting this K API here. And if we go to definition on that, we can see here for when we have MSC ver, meaning that we're using Visual Studio, then we basically say if we're exporting, in other words, we're building a DLL, which is what we're going to be currently doing, we are going to prepend this declspec DLL export. And so basically symbols, which would be the names of functions, things like that, are not exported by default. They are only exported on a Windows build if you actually put this declspec DLL export. Now, of course, you can change that default, but that's not really something we want to do, right? Because we don't really need to be exporting everything. That's really, in my opinion, sort of the ideal behavior that we want. Now, the issue is with GCC and Clang, which is basically a drop-in replacement for GCC, the default behavior is the opposite, right? And so the default behavior is to export everything, which is not necessarily what we always want. And what this has led to is I've forgotten a couple of K APIs throughout the code base, and then Windows people go, oh, I can't compile this. And that's because when they go to build it on Windows, they don't have this declspec, right? And so when they go to link it together, it's a undefined symbol and they can't build it, right? And so I did a little bit of research and came up with a way to kind of configure Clang / GCC to basically do that same behavior so that we don't export things by default. We only export them if we have this attribute visibility default, right? And the funny thing about this is the Windows version is kind of explicit, right? DLL export. That's pretty explicit as to what it's doing. Visibility default basically means public, right? So that basically means we're exporting that symbol, right? And so up to now, we've had these K APIs, right? And we've been putting this attribute visibility default, but this visibility default is already the default for everything. So it doesn't really make a difference, right? And so we're going to change that today. And there's it's kind of a two-step process because of the way that all of this works on Linux, and it's also a little bit similar on Mac. And so on Linux, which is what I'm on right now, we'll cover that first. And basically on Linux, there's a couple flags that you have to set both in the compilation stage and the linking stage. So in the compiler flags, we have to include this f visibility equals hidden, right? So this takes that visibility that's here and changes it to hidden by default for everything, right? However, that in and of itself is not quite enough, right? And so what that basically does is it takes the symbol and says, okay, well now it's a local symbol, but that symbol actually still gets, the text for it sort of still gets exported. So the DLL or the SO file, right, the equivalent of the DLL, still says, hey, I have a symbol that's called this, right? But I'm not going to tell you, what that is or where it is or whatnot. It's up to the shared library itself to sort of give that to you. We're going to trust that it's there. And the problem with this is if you would go with just this alone, there's nothing that guarantees when you compile that internal symbol is actually defined, right? It could be set to static, which would mean that it's private to that compilation unit, or it could not be defined at all. And this basically just allows us to define it in a header file and link against it. And it says, hey, you know what? We're going to trust that it's there, or it will be there, provided there by some library somewhere, right? And obviously the issue with that is there's no compile time check to see if that actually exists. In Windows, you would hit that issue right away. When you compile, it wouldn't, or I should say when you link, the linker just wouldn't see it, right? In this case, the linker sees it, but it doesn't know that it's not defined, right? And so there's an additional step that we have to do outside of this, and that's in the linker stage, right? And so we actually have to pass this this linker flag. There's two linker flags, actually, where there's no undefined and no allow shlib undefined, right? And the long and short of this is that these essentially reach in and check to say, hey, does this thing actually exist? Is this actually defined? If it isn't, it then throws a linker time error to say, hey, you've told me this thing is here, but it's not actually there. What are you doing? And so the combination of these two things, hiding the symbol here, which essentially turns it into local, and then also making sure that it's defined, will give us that same behavior. So I've put some comments in here as to exactly how this works, right? And then also I had to dig quite a lot for this because this stuff isn't very well documented. And so I put a solution here, and ironically enough, it wasn't even on a C issue that this came up, right? It was actually under the Ziglang that I found a solution for this, right? But that, sort of uses C under the hood. And so I was able to take that solution from there and use it here, and it works, okay? And so for Linux, that's basically the way that works. For Mac, it's almost the same thing. And I haven't had a chance to actually test this yet, but I'm pretty positive it's going to work based on what I've read. So we still need to set visibility hidden, right, on the compiler. But this time, instead of no undefined and no allow shlib, which is shared lib undefined, all we have to do is put dash undefined comma error, right? And we pass that to the linker, and that should do it, right? So it should give us the same behavior now across all three platforms, and we should be good to go on that. So just to prove that this all works, and that you guys can see exactly what will happen if we don't have this in place, I'm going to do two things, right? So this plain 3D create is actually referenced by the test bed, right? So if we remove this K API, right, and we do a clean, and we do a build, it's going to build with the engine fine, the Vulkan renderer, all that stuff fine. But when it gets here to the testbed lib, it's going to say, hey, we don't know where this thing is, right? We have these undefined references to plain 3D create, right? Which is exactly what we want, right? It's now reaching in and verifying that that symbol is at least defined somewhere, right? And so if we go ahead and put that back, right? And I'll do a clean and a build again just to sort of prove this, right? If we go ahead and put that back, it works successfully, right? It's able to link. So the second part of this is to obviously check to make sure that this works within a library, right? So I know for a fact that based on some changes that I've made recently, let's see, where is... Oh, I think I did that in a branch, actually. Let's see. Which one of these is used in the Vulkan plugin, for example? Let's see. Let's go to the Vulkan backend, and let's do a vec3. Why do we not have anything there? Maybe mat4. I'm just looking for a function here, right? Actually, I think all the matrix functions are all in line. Do we have... What's a function in here that we are using from... We have math types. Are we actually using this at all? I'm not sure. Let me see. I guess we could theoretically test texture system, right? So if we go in here to texture system, whoops, I need the H file, right? And we do, let's see, what is get default texture, right? That'll work. We know we're calling this from within the Vulkan backend, right? So get default texture, right? So if we remove this guy here and we clean and we build, now what's going to happen is the Vulkan plugin won't build, right? For the same reason, undefined reference, right? So this solution works both for libraries and executables. And so with that, one last thing that I want to bring up is if we go back a moment into our build file, and we get rid of this this undefined, right? This bit that checks for it, right? If we get rid of this and we go ahead and build again, notice that it successfully builds, right? And actually, even to prove this further, I'll clean and build, right? So we still have this undefined over here, right? We still haven't exported this symbol. Notice it still builds, right? If we go to run this, like if we go to, whoops, I'm in the bin folder there. Right, so if we go to run this, what we're gonna get, it compiled fine, right? But look what we get in here. We get a runtime error. Error opening library, render SO, undefined symbol, right? So if we didn't have that, we would find that out the hard way at runtime, which is really annoying, right? So that's definitely not what we want. Coffee Lava, welcome, and thank you for the hydrate. How's it going, man? So this is definitely not the way we want to find out about undefined symbols, right? Definitely not it. So if we go ahead and put that back, right? And then I'm not going to build clean again, right? Because it's just going to, right now it's going to complain about this. Actually, you know what? Let me prove one more thing. I'm going to undo this again. All right. Build this again. I'm going to flip over here and go into the bin folder. And I'm going to run, what was it? NM, right? Which is basically going to tell us what all of the symbols are exported. And I'm going to just run that against lib engine.so. And basically what this gives us is a list of all the symbols that are exported, right? And basically the ones that we're interested right now are the ones that are in the T section. So you'll notice that there's capital T's and there's lowercase t's. The lowercase t's are ones that exist, but they're local to that particular compilation unit. The ones with the capital T are the ones that are exported, right? And so we can actually grep this. And we can use what was it? Texture system get default texture. Right, so texture system get default. Oops, if I could spell default correctly. Right? And so if we do that, we can just get the one entry to see, hey, we have a lowercase t here, right? If we flip back and we put the K API back and build this again and run this again, right? Notice it's a capital T, right? So that means that it's definitely exported globally, essentially, right? And so this is essentially what we're looking for. Now the difference is we can also pass the uppercase D flag, which basically tells us dynamic, right? What's available to us when we load this thing dynamically. And if we run grep against that, notice we get a T, right? But if we were to remove that again, right? Switch it back, run it with the capital D again, notice nothing comes up. So that is basically the difference that we're looking for, right? That is essentially how we're looking at it. And so when we put this back, it's basically kind of doing the same thing under the hood, right? It's essentially looking for it in a similar fashion. And so by doing this, we're going to catch those errors and no longer have that inconsistency between how it builds on Windows versus how it builds on Linux, right? So now if we put this back, which I think was redo? Nope, undo. So if we put this back and build again, notice that it works, right? And if we go back to code at this point, it works, right? So that is basically the extent of that change, right? So there's a couple things also that I added in addition to it. So we have, actually I messed with a couple files here and make sure I didn't break anything. Okay, so the executable and library both have changes. And I also fixed a couple small things that I found in debug console and Vulkan backend. So we'll kind of look at those too. So we'll do a diff on this real quick. And so we can see here, we removed this compiler flags line, or basically replaced it with this guy, right? So we're doing F visibility hidden here. And then here we've added the no defined and no allowed share library undefined, right? Keishin, thank you so much for the follow. Appreciate it, and welcome. I'm doing pretty good, Coffee. Can't complain. Just, kind of looking at some different stuff tonight. Instead of just UI stuff, because I know we've been doing that for a bit. We're going to kind of take a little bit of a detour tonight And instead of just that, we're actually fixing our build process to make it consistent across platform, which is what all this symbol stuff is about. So basically, symbols now don't export by default on Linux and Mac, essentially, is what it is. So we have consistency in our builds between the three, and we don't have missed KAPIs being, not added where they should be, essentially. All right, so that's that. And then, that's for the executable, and we made the same changes in the library, right? At some point, I think I'm going to wind up combining those two makefiles into a single makefile because they're almost identical. There's just a few differences. And so I think at some point it makes sense. I might be able to actually combine those two and simplify into one. All right, so the debug console, all this stuff up here is just essentially stuff being moved around for order of includes. One thing I was doing here that actually I caught while I was test compiling this in GCC was what we're doing basically here is we're saying state history offset is the minimum between that incremented and length -1. And the problem is it's ambiguous as to which operation happens first, this or this. Like it doesn't know, there could be the potential that could be wrong, right? And so instead of modifying it directly like this, we're saying offset +1. And we're taking the min of that, or length -1, and then setting it to this guy, right? So we've done that there. And then for some reason, in Vulkan backend, we were doing a multiplication here instead of anding these together, right? I'm thinking that was just a typo because they're like literally right next to each other in the keyboard. But I never picked up on it before. So I just happened to notice that and fixed it. And I think, the other thing is GCC actually bleated about this not being used, which it really wasn't. It was being set here, right, in all these places, but we weren't using it. Eventually we are, so I just commented those out. We let you cook. Yeah. Cooking with fire tonight for sure. Got some cool stuff. All right, so this one, I'm not even going to make a feature branch for. I'm just going to made symbol exports consistent or consistent, I think, across Linux and Mac OS to match Windows. God, I can't type Windows. I should have just left it DOZE anyway. All right. Did I not? Oh, I'm in the bin folder. What a dingus. Okay. And let's go ahead and push this up. All right. So that is available on the main branch now for you guys to pull. So that was definitely a long-standing thing that I've been meaning to tackle, and finally tackled. So that's awesome. Okay. So the next thing we're going to do is we are going to check out a feature branch that I made. Actually, you know what? Before we do that, we've already built this. So I want to run this real quick and show you what we're actually going to be fixing. So this is a 4K monitor that I'm on right now. And I know you guys over Twitch can't really see that because it kind of forces me to downscale it to 1080p. But if we load this in 4K, especially on the terrain, this is painfully slow, right? Especially if we look out over the terrain, right? And we don't have that much going on here, right? So why the heck is this so slow, right? Like, we're getting 16, 18 frames a second. Like, that's terrible, right? And even when we spin around and look at this guy, like, our frame rate just tanks, right? And if we look, if we move the camera a little bit, which I really need to make this variable speed eventually so we can move fast, right? And we get really, really close, right? If I look directly down at a really close altitude, right, we see that we get 60 frames. And if I turn VSync off, we get about 80, 90 frames, right? Which sounds great, but it's not really that great, right? Like we're literally just looking at some terrain here. Like this should not be that heavy, right? And of course, if we look out here, you know, our frame rate tanks. Like this is not the way that this should be working, right? And so you could say, well, you know, maybe we're generating, we're rendering a lot of polygons, but we're really not, right? These textures are kind of high resolution, right? And that's really the what the crux of the issue is. If you look out, you can see that no matter how far back we go, we're using the full resolution of that texture. And we're blending between 4 textures, right? So for each individual fragment, we are basically sampling and using the entirety of those high resolution images, which when you get back here is completely unnecessary, right? And so what we're going to do is solve that, both for performance reasons, but also it's going to kind of clean up how this looks in the distance, right? Because it doesn't really interpolate all that well when you're looking this far away, right? This is really noisy and stuff like that, right? And so there's a way to actually get around this. And we're going to take a look at that now. And that way around it is something called mip-mapping. And actually, let me see if I can pull up an example. All right. So, what a mip-map is. Here's a decent example of it. Right, this is actually off of Unity, right? But it serves the purpose. Actually, let me see if I can just open the image by itself. All right. I'll blow this up a little bit. I realize it's going to make it blurry for you guys, but I think you'll get the point. So what mip mapping is you basically take the original texture and you cut its size down by half per level. So you have these different levels for different types of textures, right? And what this does is basically the further the texture gets away from the camera, the lower version of it we use. So we're basically cutting the resolution in half every single time, right? Or technically we're cutting it by 4, right? And so for each MIP level, we step it down by half, right? So this original texture is 128. We step it down to 64, 32, 16. We can go all the way down to 1 pixel if we want to, right? Let's see. Oh, Mfata. I hope I pronounced that right. Good to see you as well. It's almost 4 a.m. there. Jeez, where are you? That would put you what? 8 hours ahead? Egypt. Oh, cool. Well, I'm glad you're here. So welcome. Yeah, I was trying to figure out exactly how far over that was, but yeah, Egypt does make sense. Okay, so this is basically what we're going to be implementing tonight. And actually, I've already technically done it ahead of time, just because Vulkan gets a little bit tricky about this, and so I figured it would probably be easier to kind of go through it in retrospect and explain it that way. So this is what we're going to be putting into place, right? So when we look out at that terrain, we're going to be looking at the lowest version of this MIP, right? And so we can get rid of this guy. And so what we are going to do is we are going to we're going to run this first so that you guys can actually see this in action, right? So we're going to check out feature Mipmaps, right? And we're going to clean and build. And this is one of the rare occurrences where I'll actually be able to show you the results before we actually do it, right? So if I go ahead and run this and maximize it as before, load up level, we can already see, before I even turn VSync off, that it's much, much better, right? And so, like, I can look out across this, and we're already getting 60 frames per second. If I turn VSync off, that number goes a little bit higher, right? It's 72. It's still not perfect, right? There's still some optimizations we need to do. But one thing you can notice right away, too, is that this is all much, much smoother, right? And that's because we're sort of scaling down and using those lower resolution versions as we're going, right? We got ads. So we just got 2 minutes of ads here, and then we'll continue. I just like to pause the stream for anybody that does have ads come up so that nobody misses anything. So for those of you guys who can still hear me, just bear with me here for a minute, and we will continue here in just a moment. Got about 40 seconds left on ads, and then we can continue. All right, and we are back. PFK, thank you so much for the follow. Appreciate it, and welcome. All right, so obviously, all this stuff in the distance is all smoothed out, and if we go into some of our other rendering modes here, we can really see that action, right? Especially with this normal here that is more rough, you can even kind of tell that it's kind of scaled down the further back you go, right? So that's that. And actually, even if we spin the camera around and kind of look at this guy, which has, this is a pretty high poly mesh, as well as this has got about 300 sub-meshes in it. I think did we have a count on here? Yeah, so the number of drawn is 395, so it's almost 400 meshes we're drawing on the screen right now. We're still maintaining a decent frame rate, right? And obviously there's some optimizations that we're going to do eventually with the terrain. Things like chunking it and whatnot to get that a little bit better, right? But this is sort of the first big optimization that we're doing that really hits hard, right? So we can definitely see that we have a pretty substantial improvement in performance here. So that is the crux of what we are going to be doing tonight on this. So what I'm actually going to do is I put up a pull request. So let me pull that up. Let's see. Here we are. So that way we can kind of take a look at the... oh, am I not logged in? Really? This is what I get for doing an update right before stream. Bear with me a moment. I just gotta sign into GitHub. Okay. All right, so pull requests. All right. So if we go ahead and take a look at the files changed, right? It's not too crazy of an amount of changes. There were a couple supporting changes we had to put in place. So the first one is we needed a floor function, which basically just gives us the closest integer or the largest integer less than or equal to x, right? So if we have 4.6, it'll give us 4, essentially, right? And then we have k log 2, which essentially gives us the base 2 logarithm of x, which basically means how many times can x be divided by 2, right? And so these are needed because we're essentially going to take the resolution of a texture and run k log 2 against it, grab the floor against that, right? So we're going to say, how many times can we half the resolution of this particular texture? And then take the floor of that so we have a whole number, right? So that's what those are for. For right now, those just point to the math equivalent of those things, right? The clib math lib, right? So eventually we might implement our own as sort of a learning exercise, but for now it's just kind of forwarding onto that. All right. So one thing that we did, and you know what, let's hit resource types first. I'm going to kind of collapse these as we go too. Otakumaru, thank you so much for the follow. Welcome. So one of the first things we did is we made a couple of modifications in resource types. So our image resource data, when we actually load an image from disk, we are going to calculate the MIP levels at that point, right? MIP levels is always going to be at least 1 because the number of levels we have is always going to be at least 1 because we have a base image, right? So there are going to be circumstances where we don't necessarily want to use mip mapping and we can turn that off, but that number is still going to be 1 in that case, right? So we're going to have some code to make sure that that is always 1, right? So anywhere you see MIP levels, essentially, this comment is going to be basically the same, right? It's always going to be at least 1. So this is when we load the image resource from disk. We also added this to the texture structure, right? So the texture is aware of how many MIP levels it has. And then the texture map also has a couple things added to it. So it has MIP levels, so it kind of caches the MIP levels of the texture that's assigned to it. And it also keeps a generation. Now, you'll notice that it goes hand in hand with the generation that we have on a texture. So the reason for this is anytime we reload the texture, like if we hot reload a texture, which eventually is going to be a thing, or if we're in the process of loading a texture and we use the default texture until the real one is loaded, this generation comes in handy, right? It comes in really important. And so what we always want to check is that the texture maps generation is synced to the textures generation, right? And that the MIP levels are also synced. And if either one of those two things are out of sync, then we're actually going to have to regenerate the sampler because the sampler is one of the things that says, okay, we have these mip maps, how do we use them? So there's that, right? And that's the high level changes for resource types. All right. So the first place that we want to look is obviously the image loader. That's the first thing that we kind of touched on, where we have the usage of the kfloor and klog2 that we mentioned before. So basically what we do is we grab the width and height, and we grab whichever one of those is bigger. And if they're equal, it just doesn't matter which one we grab, right? We run klog2 against that to say how many times can we have this. We grab the floor of that, right? So if that number could potentially wind up being 0, right? If the texture is 1 pixel, right, you can't divide that by 2. That'll be 0 essentially. So we take whatever that is and add 1 to it so that we always have at least 1. So you're going to see this algorithm one more time, but that is basically the way that we handle this, right? So we calculate that out. And then in, let's see, in font system, I actually just fixed a typo. So acquire was spelled wrong. So I happened to notice that while I was doing some refactoring and just fixed that. Texture system, these includes just kind of got reordered, so that's not a big deal. Acquire was spelled wrong here, right? So I just fixed that. But the main thing that we did was down here, when we are acquiring the writable texture, right? We also have to be sure to set the MIP levels on that to 1. So whenever we're creating a texture, if we're not loading it, but we're creating it dynamically, we need to make sure that's set to at least 1, because generally speaking, it'll be probably zeroed out when we allocate memory for it. So we need to make sure that's set to 1. So we set it to 1 here whenever we have a writable texture, because if we're writing to a texture, we're probably not going to be mip mapping from it, right? But if we are, we could probably handle that separately. But for right now, writable textures do not use mip mapping. So mip levels of 1 basically says don't mip map this. So we do that for the default texture, the default diffuse texture, the default specular texture, and the default normal texture, right? So we set all those to 1, basically saying we're not going to worry about mip mapping these. I suppose these default textures could be mip mappable, and maybe we'll change that at some point, but for now we're not going to bother. The only thing other than that is when we load cube textures. So like for right now, that could be skybox is what we're using that for. We're also not mip mapping those. Now this is probably not always going to be the case because we are going to have cube maps that we are going to probably want to mip map potentially. But for right now, that's just kind of one, it's like a one-off thing, right? So we're not going to worry about that. We just set that to 1. When we go into this texture load job start, this is the multi-threaded entry point for loading a texture from disk. After we load that resource, we go ahead and copy over the temp texture mip levels from the resource data mip levels. And then we also make sure to set that to the out texture pointer. We set the mip levels to that as well, right? So that way both of those are handled there. So that is all the updates for texture system. Here's the misspelling fix right there for the header on that. So that's all that is. The Vulkan backend is where most of these changes exist. There and also Vulkan image, right? So I'm going to skip the backend for a second and actually go to Vulkan image, which is here. I don't think we changed the header file on this. I think it's only... Nope, we did. Let's hit the... Yeah. Let's hit the header file first so we get a sort of external perspective on what changed. So when we do Vulkan image create, we just added a new parameter for MIP levels, right? So that's the same as everywhere else. Default is 1. And then we have a new function here, which is Vulkan image mipmaps generate. So all this does is takes in a context, takes the image to generate mipmaps for, and a command buffer, because this obviously has to go through the GPU, right? And so it basically looks at the properties that are already on the image and determines from that how to generate the mipmaps, right? So that is the sort of external facing changes, if you will. If we take a look at Vulkan image C, we added Vulkan core here, which actually probably isn't necessary. I could probably get rid of that. Yeah, whatever. It's not going to hurt anything by being there. So we have our Vulkan image create that takes our new parameter MIP levels. We do a check here to say, hey, if MIP levels is less than 1, go ahead and set it to 1 and warn about it, right? And this is because we don't want to crash the application, right? We want to kind of keep things running as much as possible. So we're going to default to 1 if it's provided to be, you know, some sort of like 0 or something like that, right? And so we go ahead and we set the out image, which is the Vulkan image MIP levels, to the passed in MIP levels. And we also store off the format on the image because we are actually going to need that when generating mipmaps, right? So we now store the image format which we weren't storing before. We store that on the Vulkan image now. Okay. So a little bit further down, when we are filling out the image create info, I removed some to-dos here because these things aren't really to-do anymore. So this one is to-do, right? We still don't have configurable depth, but we don't really need that right now. But the important one is this out image mip levels is now set to mip levels here, right? And so this is what is going to tell us when we're creating that image, how much memory to reserve, things like that. So we set mip levels there. And then when we're creating the view, we also have this level count, which was hard-coded to 1 before. That is now going to look at mip levels as well. So the level count is for mip mapping levels, right? So that's where that belongs. So when we create the view, it needs to know about that as well. When we are transitioning the layout, we had a level count here. We now also have a mip levels here. So when we transition the image format from, not the format, the layout rather in memory. When we transition from one layout to another, we need to know how many mip-map levels are we translating as well, right? So we have that. And then the meat and potatoes of all of this is this mip-maps generate function. And it looks like a lot of code, but it honestly really isn't once we break it down. So let's do that. So the first thing is if we have mip levels less than or equal to 1, then that means we don't need mip-maps, right? So we're going to warn about it saying, hey, we're trying to, we called mip-maps generate on something that doesn't really need it, right? And we're just going to return false because there's no sense in running through this code if that's the case. The next thing is we are going to check to see if the image format supports linear blitting. Blitting is how we are going to create those half-size images, right? We're just essentially going to blit them straight to memory. And so we're checking to make sure that linear blitting is supported. And if it's not, then we're basically going to skip the process of making mip-maps at that point, right? So we're basically looking at optimal tiling features and seeing if it has that image filter linear bit set on it, right? I've not seen a case where this isn't true, but it technically, according to the spec, it could not be supported, right? So we do want to keep an eye on that. So the next thing that we do is we create an image barrier, and we can technically use this same barrier for all of our MIP levels. We just kind of change some things along the way. And so that's what we're going to do. We're going to create this at the top. We're going to set the S type, the image handle, the source and destination queue family indices, it's going to use the graphics queue. We need to use the graphics queue for this. Because of the blitting operation, we need graphics. We can't just use transfer, right? And so this is all going to look very similar to our transition layout, right? And so where transition layout sort of does this operation once with a memory barrier, in this case, we're going to do it multiple times, right? And so therein lies the difference. So a lot of this is the same as there. And what we're doing is we're saying layer count is still going to be 1. Level count is also going to be 1 at this point. And you may be saying, well, wait, we changed that to the mip-map count before. Bear in mind, we're going to use this barrier multiple times. So we're going to use this once per mip-map that we generate. So since we're generating them one at a time, we are going to use 1, right? We're going to take the MIP width and height, and we're going to start that off to be the image width and height, right? And this number is essentially going to get cut in half every single time we run. So we're going to iterate each of the levels, right? Starting at 1, right? That's very important here. We're not starting at 0, we're starting at 1, because remember, our MIP level 0 is our actual image, right? So we don't want to do anything with that. And essentially what we're going to do is we're going to have our sub-resource range. The source of that is going to be the previous level, and the destination is going to be the current level that we're on. So we're starting at 1, right? Which means that our first source is going to be level 0, which is our actual image, right? So we're going to use level 0 as the source, and we're going to cut that down and blit that half-size image onto our current level index, okay? And that's basically what we're doing here. So we first transition the format, not the format, the what's the word I'm looking for? The layout, right? The memory layout. We transition that to something that is appropriate for transferring, right? And so we go ahead and perform that transition. And then we set up the blit process. So the source offset is always in the upper left corner, right? So we're going to start in the top corner of the image. And then we have the extents of the source, right? So source offset 0 is basically where we're starting within the image. And source offsets 1 is where we're ending in the image, right? The extents. So this is for the source material, right? And the source aspect is color bit, right? The source is the previous level, right? So we're going to take I minus 1. So in the first loop, that'll be 0, right? Base array layer is always 0. Layer count, again, is 1. And then here we set up the destination. So the destination, again, is going to be top of that sub image, right? And then the offset is going to be, well, if the mip width is greater than 1, then we're going to take the mip width and divide that in half and use that. Otherwise, we'll use 1, right? If the mip height is greater than 1, then we'll take the mip height and divide it by 2 and use that. Otherwise, we'll use 1, right? And then we'll have 1 for the Z, right? Because we have 1 there, just like here, right? We have 1 layer. And otherwise, these things are mostly the same. It's just pay attention to the fact that the mip level here is I for our destination, right? So our source is I minus 1. Our destination is I, right? These two things are the same. These two guys. Okay. So we take all that information, we say blit it, right? And then once we've done that, we transition it to a shader readable layout, right? Which is what would normally happen when we are loading up a texture, right? After we've loaded it from that memory and transferred it from the staging buffer, we would normally perform this step, right? But what we're transitioning here, if you pay attention, is actually the previous image, right? So we're transitioning the previous level, which in this case would still be 0, to be used in the fragment shader, right? And so we do that. And then here is where we actually split the width and height in half for the next level. So if there's another level to do, we'll use this, right? So we just say width divided equals 2, height divided equals 2, right? And then we just loop again. Now, this last pipeline barrier transitions, remember, the previous mip level's resource, right? So once we complete this loop, that last mip layer won't be transitioned to the right layout. And so what we need to do here is handle that, right? So we basically just say, hey, take our last mip level, which is this mip levels minus 1, and perform that same transition on that. And then we're done, right? So it looks like a lot of code, but really all it is just kind of filling out this struct, right? There's not really that much here. It's not really that complicated. And I tried to comment it so that it's very obvious as to how all this works. All right, so that is how we generate the mipmaps, right? Nothing, I don't feel like, too complicated, right? I think that's pretty straightforward stuff. So I'm going to touch on these couple bottom files and then we'll go to the backend changes, right? So we needed in Vulkan swap chain, when we do a creation here, let me expand this a little bit. So when we are creating the swap chain images, right? And I think this is actually, I think these are the depth textures actually. Yeah. So when we're creating the depth textures, we have to say, hey, we don't, we're still calling image create, but we don't want to mip-map that, right? So we're going to pass 1 there. So that's all that does. And in Vulkan types, as we mentioned before, we on the Vulkan image, we store the format and the MIP levels, right? So we've got that. So the remainder of the changes are in Vulkan backend, and there's one new sort of public method. We're not exposing this yet to the front end. I don't think it needs to be, but you know, we can expose that if we want to. So basically, what this is it's a refresh texture map resources, so we can recreate the sampler if we need to for a given texture map, right? So that's just the entry point for that, and we'll go into that here in a minute. So the last piece of this is in the Vulkan backend. When we are doing a render texture create, we're passing through the texture MIP levels to Vulkan image create, right? So we've got that. And then when we're doing a writable texture creation, right, it's the same thing. We're passing through the MIP levels on that, right? When we are doing a texture resize, this is where we're going to see that algorithm again, right? So when we resize the texture, we're going to have to say, okay, well, we've got this new size texture. How many MIP levels should we actually have on this guy? And so we go ahead and recalculate that and set it at that point. And so that is that, right? We only do that, though, I should mention, if we were using MIP mapping in the first place. So if MIPs are set to 1 on the texture, meaning we're not MIP mapping it, we don't bother doing this, right? So there's that. And then when we call the image create on texture resize here, right, we just pass through the MIP levels there. Transition layout now also takes, let's see, what was that? Right. So when let me expand this up a little bit further. So when we write data to a texture, we have to grab a staging buffer, right? We then transition the layout, right, from whatever layout it's in to being optimal for a transfer operation as a destination, right? We then copy in the buffer that we want to write. And then before, we would transition from that to a shader read-only optimal, right? And we just transition it back. We can't necessarily always do that here, though. And the reason is because if we've written this data and that image is mip-mapped, we may need to regenerate the mip-maps, right? And so what we essentially do here is we say, well, if the MIP levels is less than 1, then we go ahead and just transition it as normal. If we are greater than 1, but fail to generate MIP maps for some reason, then we go ahead and just transition it as normal, right? So that way, at least we kind of catch both scenarios there with the same block of code. Okay? All right. So when we apply let me go here. So when we apply the shader instance, right, and we're iterating the samplers, one of the things that we have to do is we have to check at that point the texture maps generation against the texture generation as well as the MIP levels, right? So those things that we put in there on the texture before, this is where we actually make that check. So before, all we basically did was this block minus the generation bit. So we would say if the texture generation is invalid ID, that means that we're using the default texture, right? So we just get the default texture, and that's what we did before. However, if that's the case here, we also make sure to set the maps generation to invalid ID, right? Otherwise, if we are not invalid ID, right, then that means that we have a texture that's been loaded through the process. And that means that the map and the generation could be out of sync, right? So the next thing we do is we check to see if those things are in sync. If they're not in sync, then we say, okay, well, are the MIP levels different? Did the texture MIP levels change on the reload of the texture? And if they did not change, then we don't need to do anything, right? Because we should be fine at that point. We don't need to regenerate resources for that, right? The mip map should just be a drop-in replacement. However, if they are not the same, then that means a refresh is required, right? And so we just put a little trace message out here to say, hey, this is what the MIPS were, this is what they are now. And then we say if the refresh is required, but for some reason we fail to actually perform that refresh, then we warn about it, right? But at that point, it still shouldn't be enough to actually cause us to crash the application, right? So we want to know about it, but we're not necessarily going to worry about it just yet, right? Otherwise, if a refresh is required and this succeeds, or a refresh is not required, either way, we sync the generations, right? So that is where that syncing code is. And then the rest of these are just actually using the mipmaps, right? So what we did was we had this texture map resources acquire, and this was responsible for creating the sampler. And we've moved that code into a static create sampler method because we're going to need this in more than one place. And this is the same code as before. The only difference is we have the MIP levels, right? And then in our sampler create, our min LOD is 0, but our max LOD has changed, right? And so our max LOD should be equal to the number of MIP levels we have. And that's how the GPU knows how to transition between those MIP levels as we go off into space, right? And so I also have a note here if we want to see the lowest MIP level, which I can activate this and show you guys what that looks like. We can actually set the min LOD to the max MIP levels, right? Or 0 if we don't have them, right? And so I can activate that here in a bit and show those to you guys. Here we go ahead and create the sampler. That hasn't really changed. I just moved it to one line. Same with this error case. Move that to one line. And then we return false or true, right? That's pretty self-explanatory. So now all our acquire does is calls create sampler, right? And just passes through what it normally passed through. And then if that fails, we return false. Otherwise, we continue doing the same thing we always did and return true, right? Releasing is the exact same thing, right? The only change here, I just moved that to one line. The new function that we have, and this is the last piece of this logic, right, is the refresh function that we added. So basically what this does is it says, okay, well, if we have a map and that map has internal data, then we're going to create a new sampler. So we're going to call create sampler again. And we're going to save that off to a temporary sampler here, right? We're going to take a pointer to the current sampler. We're going to make sure the device is idle. Then we're going to assign the new sampler, right? So we're going to say map internal data is the new sampler up here that we created, and then pull out the old one after that, after it's not assigned anything. And this should keep us from trying to use that old sampler when we shouldn't be, right? And I'm not 100% sure this is necessary, but I'm doing it as sort of a safety because these operations are quick enough where it shouldn't really matter. Right, and that is it for the code changes. That is the entirety of it. So if we want to, really quickly, we can go to backend, and the min LOD, I will swap over real quick and build so that you guys can see what that min LOD looks like, right? We could technically use this to look at each individual level if you really, really wanted to. So I'll maximize this and load. And now we can see here, this is what the minimum LOD mip-map looks like across the board, right? And see here we have, you know, a pretty substantial increase in performance, obviously, right? And so that's what that minimum looks like. So a lot of times what you're seeing, like when games are loading, is sometimes they'll load in the MIP, the lower MIPs first, and present that to you, and then they'll sort of stream in the higher ones afterwards. And so we might actually wind up doing that in the future, but for right now, this is what we've got there, right? So, let's see. Edgar, thoughts on WebGP? I assume you mean WebGPU? So WebGPU, I think, is going to be pretty awesome. As you guys may or may not know, on my YouTube channel, I did a lot of stuff with WebGL. Back in the day, it was, God, I guess that was what, 5 or 6 years ago at this point, I think. Yeah, so it's been a while since I've done that, but yeah, I think it would be really cool to actually write some WebGPU stuff. So I think once that has a little bit wider adoption rate, I guess, across browsers, and once it's really more widely available, I'll probably start messing with it. I know there's some libraries out there that have already done it. So I think at some point I'll probably write like a small project for that too. Maybe we'll write a game in it. Yeah, we'll see. I definitely want to take a look at it for sure. Edgar, thank you for the follow. I appreciate that. And welcome to the stream, by the way. Okay, so that is that. I'm going to undo that now. And I think I saw up here, where was that? Where did we have Vulkan image? I thought we had another. This Vulkan core, I think, was what was added. You know what? I'm going to leave it there. It doesn't really matter that much. All right, so get status. Nothing. Okay. So this actually should be good to merge in, just like it is. So I'm going to go ahead and merge this into main. And that will resolve 196, which is this guy. It was something on the roadmap, right? And now that's closed. So we now have mip-mapping, which is another item we can cross off, which is cool. All right. So that is mip-mapping. And the next thing we're going to take a look at is probably the bigger feature of the night. Believe it or not. Oh, thank you for the stretch redeem. I need that. We've actually got, we have ads coming up here in a minute or two. So I'm going to switch over to that branch and merge things, but I'm not going to start my explanation until after the ads, I think. So let me go to git, check out main, pull the updates on that. Right, so there we go. We've got that in place. So we're going to do feature audio, which is the next thing we're going to talk about tonight. Let me just make sure that I have the latest on this. I think I do. But I've kind of gone back and forth between platforms, so. And I'm going to git merge main. All right. And so that should be good. And we're just going to push that up to the branch, actually. This already exists on the server anyway, so we're just going to push that. And I'm actually just going to go ahead and create a pull request for this. Audio into main, and then we'll get to the explanation. As you can see, I did a lot of work on this, right? So this was one of those things that was kind of a large experimental feature that I wasn't even really sure was going to wind up being production ready, but it wound up being production ready. So that's cool. So let's do We'll open this guy up first. Oops, I see something I missed already. All right. So there are some cues into here as to what we're dealing with, but like I said, the ads are about to hit here in a second, so I'm going to hold off on my explanation. I suppose what I could do though is, yep, there's the ad break. So we just got about a minute and a half on the ad break, and then we're going to jump into audio. Got about 30 seconds left on ads, and then we will get going. All right. So, audio. You know what? I'm actually going to stop the music here because we're going to need to hear things. Okay, so the first thing I'm going to do is clean, right, and build. And I think just like before with the mip-mapping feature, I think I'm going to demo it first, since I've already kind of done that a little bit. On previous streams, kind of teased that a little bit. I think I'm going to demo it first, and then we'll get into the implementation, right? So we've gone ahead and build there. We'll go ahead and run here, right? And what we're looking at here is we have music playing, and we have sound that is spatial, right? So we can have this moving back and forth. And it goes from left to right in the speakers, right? We can also hit a key on the keyboard and play a sound, right? So that is, you know what, I'm going to actually adjust the volume on that a little bit because that seemed a little bit loud to me. So let's do I may wind up actually having to turn some of that off, but let's see. So I'm just putting something in here real quick. See, we're playing that on channel 6, so do 6, and we'll set this to, let's try 0.5, or maybe 0.4. That seems pretty loud, right? So let me try running this again and see if that's a little bit better. Not really. All right. So there may be something I have to actually do with that. That may wind up actually being a bug. But we'll look into it. All right. So I think what I might just do instead is actually just like turn down my desktop volume. And maybe that'll help. Maybe that won't be as loud. I don't know if it'll come through stream that way or not. I think it should actually, though. Yeah, that's a little better. Okay. So if you guys can't hear me over this, let me know, right? But hopefully this makes it a little bit more obvious as to what's going on. So what we're looking at here is we have audio playing in sort of a 2D space, right? And then we have this sort of fire crackling sound that follows this cube back and forth. So we get right up on it, and you can really hear it, right? And if you get here, you can hear it get closer to you and further away. Oh, I think I lowered the wrong channel, didn't I? I did. I lowered the fire, which is on 6. Let's see. The music is on 7. It's like, why can't I hear that? Sorry about that. My volume is working. Yeah, there we go. Okay. So now you guys can really hear sort of the difference, right? So you've got this fire effect that's following this cube back and forth. Left channel, right channel. And if I move my camera around, right, it does it from the other way. Or if I stand here at the end, you know, we'll hear it kind of in both ears, right? And so we have spatial audio working. We have 2D, what I call 2D audio working, which is the ability to just play sounds, right? So if I hit the F key, we get that. And I actually have this playing on different, at different volumes on different channels. So as we hit that multiple times, you'll hear a difference in volume. So I'll just hit that a bunch of times real quick. Right? And so that is the implementation, or I should say the feature as a whole, right? Obviously, we're going to be adding things like effects and stuff like that. This is our first pass at audio. So audio is a really large topic, actually, when it comes to games, and it can be a super complex, complicated thing. And it was no exception when we implemented this, right? So what we have is, when we're talking overall architecture of it, we have in the engine a new system, which is our audio system, right? And so we have that, and that is sort of the engine's interface into our audio system. So we have an audio system there, and that system interfaces with a plugin that we're calling Plugin Audio OpenAL, right? And so this is a audio plugin. It doesn't necessarily have to be the only audio plugin, but this is a audio plugin that the engine will come with, right? And so this one uses OpenAL under the hood. And so OpenAL is kind of like OpenGL for audio. And the reason that I chose to do that is because it abstracts a lot of the low-level operating system specific stuff away and just sort of lets us deal with the audio as a whole. And the reason I decided to go that route is because there are so many different audio systems on all the platforms, and none of it's consistent whatsoever. So to give you an idea, OpenAL itself isn't even just one thing. There's something called OpenAL, and then there's something called OpenAL Soft. OpenAL is actually owned by Creative Labs, who are the ones that made Sound Blaster and all that stuff, right? And then OpenAL Soft is an open source implementation of OpenAL as a standard, right? And so the idea is that OpenAL was supposed to be the equivalent of OpenGL, and initially it was open source, but then Creative Labs sort of scooped it up and made it a proprietary solution. And that's why you have OpenAL Soft, which is the open source version of, or open source implementation of OpenAL without all of the creative specific proprietary stuff under the closed source hood, right? And so the interface between those two is the same. The only thing that differs there is the implementation. But the reason you want that is pretty well explained on the OpenAL Soft page itself. So if we take a look at this, it says this library is a multi-platform with support for Linux, Windows, Android, OS X, iOS, and more, right? Audio backends, and look at this list of audio backends. Pipewire, Pulse Audio, ALSA. Those three are Linux alone. WAS API, OpenSL, Core Audio, that's Mac. OSS, Jack, Direct Sound, Windows Multimedia, Solaris, Sound IO, Port Audio, STL2, and Null Output, right? And this actually has a WAV file writer currently implemented, right? And then it goes on to list some of the other things it supports, right? And so OpenAL itself supports all of these things too. But there is no way that I was going to sit there and implement an audio system for all of these different frameworks, right? That's just not realistic. And when you're talking Linux, right, Linux alone, a lot of these are commonly used. So there's just no way, right? You've got a lot of these are Linux. These two are Windows, right? And so this library handles all those things, just like OpenGL or Vulkan handles the sort of underlying implementation for NVIDIA GPUs versus AMD versus Intel, right, for example. And so this is really no different than that, except the support is actually much wider in this case. So while we're doing a lot of things from scratch, this is one of those things that this is about as close to from scratch as I want to get on this. And so if we wanted to make a direct sound plugin, we could do that, like for Windows, right? That might make sense, right? Or maybe we don't want the OpenAL layer between that, and we want to just make one for Windows, right? Maybe when we go to do DirectX for our renderer, maybe we can also do that. But the idea is that this is utilizing our plugin architecture, so the audio guts of this are a plugin, right? The OpenAL implementation here is a plugin, right? And so it is up to the plugin to supply the logic to the engine. The engine knows nothing about what plugin backend is being used. And so that keeps things flexible. It also keeps the engine from having to worry about that stuff. And we can just make simple calls to the audio system like, hey, I want to load an audio file, or I want to load a music stream, right? Which those things are handled a little bit differently. And all you have to do is simple API calls like this. You can set up an emitter, set some properties on it. You've got all these channels you can set, and you could just make real simple calls like this, and it just makes it very easy to use. So on the surface, that's where we're trying to get, right? We want ease of usability. We don't want to worry about what underlying sound system we're using. And that's where this sort of this architecture comes in. Okay. So I think what we'll do is we'll discuss some concepts real quick of audio in general, and what I'm talking about when I'm talking about spatial audio and things like that. So let me open up the GIMP. And we're just going to create a new image. That should be fine. We're going to take, let's go to the paintbrush. Scale this up a little bit. And we'll select, I don't know, red. It's a little thick. All right. That's better. Okay. So when we're talking about spatial audio, we've all played games where you've got maybe some explosion happening over here, right? And your character is here, facing this way, right? And so you would expect that if you are within a certain radius of this explosion, that you should be able to hear that sound go off, right? So an explosion is going to be pretty loud, right? So it would look, have a sound radius, something like that. And you would expect to be able to hear that, but maybe not at the full volume as if you were standing over here, right? And you would expect to hear that in your right ear. Versus if you were, let's say, here and facing this way, right? You would expect to hear that in your left ear, but very loud, right? Because the distance between here is shorter than it is from here to here, right? But if you were over here, facing any direction, really, you shouldn't hear it at all, or very, very faintly, right? And so this is what I'm talking about when I'm talking about spatial audio. And we're going to call this, sort of spatial audio, 3D audio, what have you. And we're really only concerned at this point about what we're going to call two-channel audio, which is stereo, which is if you're wearing headphones, left and right. We're not going to support surround sound in this, at least in our initial implementation. That's much more complicated. And so we're not going to support that with this, right? We're just going to have simple 3D sound to stereo, and I think that'll be more than enough than what we need for most applications, right? Now, that is sort of our spatial audio, and the other thing that we have is sort of this 2D audio, and that's for things like button clicks in your menu system, or music playing over, sort of the background, things like that. And that is not going to care about where you are in the world. That is just going to play at a constant volume, no matter where you are, no matter what direction you're facing, any of that stuff, right? And so those are going to have one sort of representation, and then things like this here, the spatial audio is going to have a second representation of an emitter, right? And so we're going to have an audio emitter that basically emits from a given position. And for right now, it just emits that sound, right? We're eventually going to have more fine-grained control over this as we extend this, but for right now, it's just positional. And that is going to be what is known as a source, right? So this emitter will basically, have a position in space and will be a source. A 2D sound or music is also going to be a source, but not contain spatial data, right? And so they're both what's known as a source under the hood, but they are different in how they act, right? And then we are also going to have a concept of a listener. So the listener is our player character, whether they're here or here or here or whatever. Or the listener is also technically also the listener for that 2D implementation. And so the listener, we only ever have one of, right? So it's either going to be here or it's going to be here, right? It's not going to be both, right? Or it's going to be here, right? Whereas sources we can have multiple of. So we can have another source, say here, right? And another source here, all playing different sounds at the same time. Obviously, there is a finite number of these, but we can have multiple sources all playing at once. And that's a totally valid thing to have, right? But we only ever have one listener. And so one thing that we need to bear in mind is that listener has a position, as we've talked about, and they also have a direction, right? But they also have an up direction. So if we think about this in 3D space, right? Let me actually draw a 3D graph, right? Let's clear that. And let's draw a, let's see, so green is usually up, I think, right? And then we have Z, which is kind of to the side over here. And then we have X, which is this way. Okay? And so our listener has a couple things. So our listener has a 3D point in space, right? They have a forward vector, right, which is where they're looking. And then they also have an up vector. And using the two of those, there's a whole bunch of cross-product math and stuff that happens behind the scenes to figure out, where our hearing should be picking up sounds from those different sources at different locations, right? And so when we're talking about spatial sound, we need to maintain the position of the listener, which it just so happens we already have that information because this is actually the camera forward vector and the camera up vector. So we already have those things that we can actually use and just plug right into our audio system and it'll work right out of the box. And you saw that in the demo that I gave, right? When we're talking about 2D audio, there are two ways to accomplish that. One is with a stereo sound effect, right? So if you have a sound effect or a music clip or something that is in stereo, OpenGL by default will not use spatial. It will not perform any spatial calculations on that. It'll say, okay, this is stereo. This is meant to play in both speakers, and it just does it, and that's it, right? And so it doesn't matter where you are. It doesn't matter if that sound is positioned somewhere in 3D with the source. If you are playing a stereo track, it is going to come through both speakers. If you were wanting to have spatial sound, then you need to go with a mono track, meaning it's only on the left or the right. And it doesn't really matter which one, because OpenGL is just going to take that mono and use that to spatially position it, right? The other way is if you only have a mono track for a sound effect that you want to play in 3D, then all you do is you set the position of that source to be the same as the position of the listener, and you get the same thing as 3D, or as 2D sound, right? So there's multiple ways to handle that. So at a high level, that is basically how all this stuff is going to work. So if you guys have any questions on that, feel free to jump in the chat and ask away, right? So I think the best way to look at this is probably to take a look at the sound system first. And then we can go ahead and take a look at the plugin. Glucky, first time chat, welcome. Distance to source, how does it usually affect the sound? Is it just distance to volume level function? Do people apply some effect with their level depending on the distance? So right now it's more like it's like a fall off curve, right? I forget what the exact term for that is. I'm gonna have to look it up. But basically, if you're imagining a graph, right? And one is, I don't know, like this is volume, this is distance, right? It's going to look something like this, right? Where this never quite reaches zero, right? It's going to look something like that, right? So it's not linear. I forget what the term is. I'll have to look it up. I can't think of it right now. But basically, that's what the curve looks like by default. Now, you can actually specify and change what that is. And you can also change what the fall off is, right? So you can make it really short if you wanted to, or really, really long if you wanted to. And so there are ways to adjust that. We haven't exposed those yet. We're sort of working with this default for right now, just because this is the first version of this, right? And so I plan on putting those controls in there, but for right now, this is all we have. So we do have the ability also to set volume. So if you wanted to fake it that way, you could do that through the volume control as well. Okay. one more thing I should probably touch on. We've talked about sources, right? We've talked about what a source is in terms of OpenAL. In terms of our... thank you for the follow, by the way. In terms of our audio system doesn't know anything about sources, right? It doesn't care. Our audio system works with something called channels. And so our channels basically are a one-to-one representation with a source. So each channel has a source, and you can have basically one thing playing at a time on a source. So you can have one thing playing at a time on a channel. And so we default to 16 channels, which should be more than enough, right? Because generally speaking, you're not going to have that many things going on at once. That would be a heck of a cacophony in your ears, right? And so 16 is what we're going for right now. 16 is the guaranteed amount to be supported by any OpenAL implementation. Anything over that, you're kind of taking matters into your own hands, and it might work, it might not, it might crash, right? And there's zero way to query for that, which is terrible, but that's what you get when you're dealing with 20-year-old APIs, right? And incidentally, yes, OpenAL is that old. It's actually older than that. But it's still around because it's really the only one out there like it, right? And so it's just kind of a solved problem, and there's not really a need to change it or update it, right? It's there. It does everything we need it to for the most part, right? So as far as effects go, that is also going to be a thing. So eventually we're going to have like reverb effects. So reverb is like that effect you get, like an echo effect, right? When you walk into a cave or something like that. And so we'll have the ability to set that eventually. But a reverb effect is something you actually have to write. And so I'm doing a little bit of research on how to actually write a reverb effect for this plugin. And then, we'll be able to walk into a cave and hear it echoing and stuff like that, right? So, this is very much a phase 1 implementation here. We are going to be expanding on it, but I wanted to go ahead and get it in. Okay. So, our audio system. Our audio system, on the surface, if you look, there's not that much code, right? This file has 152 lines, and this is the header file, and most of that's comments. So, basically, we have our max audio channels here, which is 16. And then we have our audio system config. And so this is the plugin. We'll show how that plugin gets loaded here by the application in a bit. But it's expected that the application loads the plugin that it's going to use and then feeds that to the engine, and then that'll come in here. So the frequency to output audio at, this actually isn't hooked up at the moment, but we are going to be able to control that as well. The channel count, this is basically the number of channels to support, not the channels that I was just talking about. That's a different channel. And I know the terminology there is a little bit weird, but this is the only time we're actually going to run into this. So this will only ever be 1 or 2, right? 1 for mono, 2 for stereo. That's it, right? Other plugins, maybe you'll have 5, right? For 5.1. I guess that would be 6, right? Because the 0.1 is the subwoofer. But yeah, so, maybe another plugin that implements that might be higher. But for this plugin, it's going to be 2. Chunk size is basically to determine how much audio data we're going to stream at a time. So when we open a long audio file, we don't want to necessarily load all of that into the sound card at once, because maybe the sound card isn't able to handle that, right? We want to stream a little bit of that at a time in as we're playing it, right? And we'll go over how that works as well. So this is what that chunk size should be when we're streaming audio. And then we have the audio channel count. Now that is the channels that I was talking about before. And generally speaking, that's going to be this number right here. But we could configure it to be less if we wanted to. So there's that. We could also potentially, if we had a different audio backend or a different plugin for a backend, we could potentially have more, right? Maybe we have a different backend that supports 32 instead of 16. We don't know. And so, just like any other system, we have an initialize that has the memory requirement, state, all that stuff. So initialize, shutdown. Our update loop, it does opt into updates. We need updates for this particular system, so we have those three. And here are the rest of the functions where we actually set things, right? So let's see. Max audio channels, does it mean that if I stand between 16 audio sources, the next one added won't be heard? So the way that this works is when you play music or a sound or something, you determine what channel you're going to be playing it on. You have a channel index, right? 0 through 15, for example. And when you indicate that, if there's something currently playing on that channel, it cuts it off and plays the next thing, right? And that's the way most sound systems work. Yeah. So yeah, if you have 16 of them going at once, the next one you would add would have to go to one of those channels and basically clobber the one that's there and play the next thing. Okay, so we have two load functions here. And one of them is for chunk loading and one of them is for stream loading. And the difference is how they are handled when we actually play them, right? And so the chunk loads the audio bit up all at once and feeds it in. So this is useful for short sound effects, short files, things like that, right? And so this one is really, you only want to use this for super short things. You don't want to use this for music, for example. For music or long sound effects, voice acting, things like that, you would want to use the stream load, which loads in a stream a little bit at a time from that file as opposed to the whole thing at once, right? This is also much more efficient with memory, right? If you think about it. So that is how we load those. We'll come back to these. We'll come back to this guy here. So that is how we load audio files, right? You notice it gives us an audio file either way. And this audio file is defined here. So it's got a bunch of things defined in it. The Travis Vox, thank you for the follow. Appreciate it. Welcome. So an audio file basically has what type of file it is, right? So is it a sound effect or is it a music stream? The internal resource, right? The format, the number of channels, and this is 1 or 2 for stereo, once again. The sample rate of that, so it might be 44 kilohertz, 44.1 kilohertz, which is that, right? And then for streaming files, we have total samples left. We'll get into that. And then we have the internal file representation, right? So there's some internal data that's specific to the file format that we're going to load. And then there's also plugin specific internal data, right? And this is how we keep those things separated from one another. And you guys will see kind of where that comes into play in a bit. Then we also have some function pointers, right? So we have this because depending on some of this data here and some of this data here, these could point to different things. So load samples basically says, okay, how many audio samples do we have in an entire file? And then we have a streaming method, right, which is used for streaming types. And then we have a method here to rewind the file once we're done playing it, right? And again, that really just applies to streaming. And again, we'll see how that works in a little bit. So we have that audio file. We'll come back to the rest of this here in a second. All right. So obviously we have a load for these. We have a close, which automatically unloads it, right? And then the next thing we have is we have an audio system master volume set, right? So with anything, with any sort of audio system, you generally have a different volume per channel, right? So you have a bunch of channels. That's where we have this channel volume set right here, where we have a channel ID and a volume. And then you have a master volume that controls everything, right? So you might have one channel set to full volume, another channel set to 3/4 volume, and then your master volume is set to half, right? And it turns everything down by that much, but keeps that relative difference between the two. And so we have a master volume set and a master volume query. We have an audio system channel volume set, which sets the volume for a particular channel. We've already seen that in action, and the ability to query that if we need to. And then here we have audio system channel play. So this takes a channel ID that we're going to be playing on. It takes the file that we're going to play, and then a Boolean as to whether or not we want to loop that effect. And so if we loop it, it'll just keep playing until we tell it to stop, right? And so we have that. And I've got some notes in here about some information that you pass with it, right? So this is basically meant as a 2D sound. So whatever we play using this, we'll essentially put that source right at the camera, or right at the listener position, and play it as a 2D sound, no matter what we pass here, right? So that is for ideal for like menu effects, things like that. The other thing that we have is emitter play, right? So this takes a channel ID again, and an emitter, which contains a bunch of information that we would need to know about that spatial audio that's getting played, right? And so if we peak definition on the audio emitter, this contains a position. The emitter itself has its own volume on top of the volume for the channel. A fall off, which isn't really implemented yet, but we have it there. Whether or not the sound should loop. So that fire sound effect that we had, that was a looping sound that was just playing over and over again through an emitter. Here is the file that it's going to play, and then it also has a source ID. So whenever we call this channel emitter play, that source ID is assigned internally by the plugin, right? Okay, so that is the channel emitter play. We also have a channel stop, so we can say, hey, stop the audio on this channel. We also have a pause and resume, so we can say pause the audio on this channel, resume the audio on this channel. The difference between pause and stop is stop unassigns the audio from that particular channel and rewinds the source, right? Versus a pause does not unassign it. It leaves it assigned, and it does not rewind it, right? So you can pause a sound and then pick it back up with resume, and it'll pick up where it left off. So that's the difference there. So we have all of those, and then this one that we skipped up here, which is our last one, which is our listener orientation set. And this is our listener position. You can think of this as your input for the sound, right? So you have all the sources out in the world, or right on top of you, one or the other. And here you have this audio system listener orientation set. So it takes in a position, which would be our camera position, a forward, which would be our camera forward vector, and an up vector, which would be our camera up vector. So we already have all of this data, right? So it just plugs in real nicely into this, and we don't have to worry about it. And this, for right now, is the entire interface for the audio system. This is all you have to interact with for the audio system. Now, obviously, we'll expand this and we'll add more things. We'll add effects and things like that. But this is basically what our audio system looks like for right now. Taman, welcome. How are you doing? Good to see you. All right. So that is that. And thankfully, the sort of implementation of this is not too different either. So if we take a look at this guy here, I'm just going to hide the file browser. If we go all the way to the bottom here, it's only 266 lines of code, right? So not too bad. I am good, Taman. Thank you for asking. Yeah, doing pretty well. So we're actually making a lot of big additions tonight. After a full week of struggling with CMake, I finally got a build system integrated with my engine. Nice. Yeah, see, and that is the reason I don't use CMake, because it takes a week to get it working. Versus, I don't know, I just like Makefiles. Ended up ditching CMake and switched to Premake. I've heard that one is pretty good. I've heard that one's much better than CMake. Simpler anyway. I think that's the one Cherno uses, isn't it? Or has he moved off of that one now? I know he said he was using it for a while. He still uses it? Okay, cool. So, before I jump into this, we're about to have ads. So, I'm going to be pausing the stream here for a couple minutes just to let those go through. And then that way you guys don't miss anything. So the issue was with WPF and .NET Core. Oof. WPF. I'm sorry. Sorry you're having to use WPF.
What in the hell?
That's what I think when I look at WPF. Just a Hank Hill.
What in the hell?
All right. So, yeah, I can see the ads are about to start here in just a second. So I'm just gonna wait. It's fine. Yeah, I mean, like I said, I've done WPF stuff before, but ads. For some reason, all of my Twitch integrations have broken tonight, so I'm having to type all this stuff manually and switch my OBS manually, and it's really annoying. So I'm gonna have to fix that too. I'm guessing it has something to do with a bunch of updates I put in place on my OS today. And I switched around some things. I was playing around with a new desktop window manager, and that seemed to hose a lot of stuff when I switched back over to Cinnamon. But yeah, we have a little over a minute of ads, and then we'll be back. In fact, I'm going to turn the music back on for a minute. Got about 20 seconds left. All right. So, on to the audio system implementation. And this really isn't too crazy. Most of this stuff is just a pass-through. But we have this internal structure that represents audio channels, right? So this stuff isn't exposed outside of the system, right? So that just holds a volume because each channel can have its own volume. It holds the currently bound sound or stream, and potentially a currently bound emitter, right, which could be used instead. And so those are really the only things that a channel needs to know about at the moment. We may also eventually hold an effect there, but I don't ever anticipate this channel structure getting too large or complicated. Our audio system state is also pretty straightforward, right? So we have our audio system config that's passed in when we create it. We have the plugin that gets passed in. We have the master volume is stored here. So each channel has its volume, but then we also have a master volume. And then we have an array of channels, which is the max audio channels, right? So we're always going to sort of stand up these channels, whether or not we use them all. But instead of dynamically allocating this and having more memory fragmentation, we're just going to stand it up as that, right? It's not really costing us that much memory. What that allows us to do is during our initialization, when we are getting the memory requirement and things like that, we can go ahead and include the size of that, and it kind of gives us the size of this array automatically. So standard things, we check the config to make sure it exists. We say that we need to have an audio channel count of at least 4. I think that's a reasonable default. If we have less than 4, we give the user 4 anyways, right? And we just say, hey, stop trying to create it with 1 or 0 or something stupid, you dingus. Take 4. And then we also check the chunk size, right? So if this is 0, for some reason, like it's not configured, then we set the chunk size to 4096 times 16. So that's a big chunk of audio, or at least it sounds like a big chunk of audio. It's actually not that much, but it's a decent enough amount, right? And this is again used for audio streaming. So we set the struct requirement and then the memory requirement, and then if we don't have a state, we return true. At that point, we would allocate the state, pass that in, call this again, do all this, and then here's where we set up the state, right? So we default the master volume to 1. That's the max for any volume. And then we go through and we set the volume to all of our channels that we're actually using, right? So we have our audio channel count for config here. We set all those to 1 as well. Let's see. We go ahead and we copy over the plugin, and then we set up the plugin config. So at this point, we kind of know what we're dealing with here. So we can say max source is 8, max buffer is 256. Actually, this should probably be... I don't know why I only set that to 8. That should probably be 16. Or we should ideally take that from typed config. Actually, didn't we? Yeah, that should be typed config audio channel count. I don't know why we didn't have that, but all right. So we take in that for the number of sources, and then we have this max buffers, which is 256. So buffers are just like data buffers that you use in OpenGL. You load data into them, and that gets fired off to the API to get used. And buffers are what a source uses to actually play audio, right? So max buffers here is 256, meaning we're going to create 256 buffers under the hood. Those buffers don't take a lot of memory. It's not a huge deal. 256 will be more than enough to handle anything that we're going to throw at it. And 256 is what is guaranteed to exist, right? So we pass over our chunk size, frequency, channel count. That is the stereo or mono channel count. And then we go ahead and we initialize the plugin and we return the success or failure value of that. The shutdown essentially just goes ahead and says, okay, plugin, shut down, and that's it, right? The update loops through all of our audio channels and says if the channel has an emitter, we're going to sync eventually all the properties, right? Right now we're just doing position and looping set, right? So I have a to-do here that eventually we need to set all properties, right? But an audio emitter is something that's going to constantly potentially be changing, right? It could be moving, like that example that we saw. So we need to make sure that we update our source and the plugin to use that position. And then if we are looping, that could be turned on or off at any time on the emitter, right? So we need to make sure that's up to date too. And ideally, we should probably do this with the volume too, right? Because technically the emitter volume could also... We should probably type state plugin source. Do we have source volume? It's source gain in this case, which is another way of saying volume. So type state plugin, and then the source is going to be index I, and it's going to be channel emitter volume. Right. Technically speaking, that should probably also take into account the channel itself, right? So that should be channel. Actually, that's going to be type state channels sub I volume. Right, we're gonna multiply that together, and multiplying these two together effectively combines them. And actually, since we're doing that, we also need to do one more thing. We need to take the master volume into account there. So typed state master volume. Right, so we're blending those three volumes. We have the master volume the volume of the channel, and then the emitter volume itself, right? Now, technically speaking, those could all be 1. We're still going to get 1. But if there are any mixture of that, we could get something, you know, in between that, right? It's just kind of a linear scale, right? So we need to take that into account. Because technically speaking, we could like tween the volume on an emitter or something, right? So we want to definitely make sure that that is set. So we do position, looping, and gain. And then we do a update call to the plugin itself. We'll get to that in a bit. All right, so audio system listener orientation set. All that literally does is calls to the plugin and says, okay, set the listener position and set the listener orientation. All we've done here is combine these into one call for the front end, so we don't have 2 separate things. But basically, this just makes 2 different calls, because in OpenGL, there are 2 different calls, right? So we just have the 2 different calls in the plugin, but the front end kind of gives us a nice single function to work with. Chunk load. This literally is just a pass through to plugin chunk load, so we'll see that. Stream load's the same thing, just a pass through. Unload, pass through. Audio system master volume query. All this does is set the out volume pointer to the value of that rather to master volume, right? When we do master volume set, we go ahead and we set the master volume, but we make sure to clamp it between 0 and 1, right? That's the range we need to keep. But since master volume affects also all the channel volumes, we then need to loop through each channel to take this into account. So we get the mixed volume, which is the channel's volume times the master volume, right? And then we go ahead and we set that gain, right? Now I suppose setting the master volume actually would cause a bug here if we have an emitter. So we probably should also say if state channels sub-I emitter, right? If we have an emitter, then mixed volume times equals state channels sub-I emitter volume, right? So now we take the emitter volume into account as well, so that way we don't get weird fluctuations there. That would have been a nasty bug. Let's see. So we have a query for that, which basically just gets the state and goes ahead and gets the volume for that particular channel. Here's the set for that. So again, let's see, we have the mixed volume here. We also need this same check. We need this same check here, right? If that particular source has, this needs to be channel ID. If that has an emitter, we need to take the emitter's volume into account as well. Let's just put a comment there. Take the emitter's volume into account if there is one. And I'll put that here as well. Okay. So we've set the volume on a channel. Play does some interesting things. So you'll notice that channel ID is an I8, right? It's a signed integer. And the reason is because we can actually pass -1. And -1 basically says use the first available channel. This is for like when you want to play a throwaway sound, you don't care what channel it plays on. You just want to play it, right? So you can technically pass -1, and it says, okay, well, if -1 is passed, that basically we go through each one of the channels and say, if there's nothing assigned to that channel, use that channel. If we get all the way through this loop and there's no channel assigned, then it says there's no channel available for playback and the sound is dropped, right? So this was maybe that one example that you were talking about, Gluki, where if everything is playing something at once and you don't specify a channel, if you specify -1, at this point it would be dropped, right? If you specify a channel, then it's going to skip all this logic and it's just going to go ahead and play, right? And so Here is where we make sure that if we're playing a sound, we make sure the emitter is not assigned to anything, and we assign the current to the file that's passed in, right? We go ahead and we set the volume, right? And so that is the source gain set. We set that to the channel volume. Again, this actually needs to take into account the, let's see, state master volume. Needs to take that into account. So we've got that. And then we say, okay, if it's a sound effect, then we're going to set the position of we're going to set the position of the source to the listener position. So this is what I was talking about anything that's played through this method is considered a 2D sound. And we get that by setting the listener position to the position of the actual sound that's passed in, right? So we get that by querying the listener position and then saying set the source to that position. And then we go ahead and we set the looping to the loop Boolean that's passed in, right? Otherwise, if the file type is a stream, we don't need to do anything, actually. So this actually could go. Okay, so we only need to do this for sound effects, right? If we are streaming, we don't need to do that. So we call source stop on the channel to make sure that nothing is actually playing. It shouldn't be, but we just make sure of that. And then we play on source with the given channel ID as the source ID, right? And so that's the way that works. Emitter play essentially does something very similar, right? So it has that -1 logic, right? And if it finds a channel to play on, it plays on that. If it doesn't, it bleats about it and drops the sound. Otherwise, we go ahead and we set the emitter, and then we set the current to the emitter file, and we play on source. Same thing as before. Audio system channel stop basically grabs the channel. Wait a minute. Why is this? Oh, right. Okay, so if we call audio channel stop and we pass a negative number here, again, this is a signed integer. So we pass like -1, right? That means stop all channels. So if channel ID is less than 0, we loop through every channel and we stop it. Otherwise, we stop the given channel. Simple enough. Pause basically does the same logic. If we pass a negative, it pauses all channels, right? If we pass a specific ID, it pauses that channel, right? Resume, same exact thing, just for resume, right? And that is the audio system. That's the front end of it, right? So I hope all of that makes sense. So the next thing we're going to look at is we're going to look at audio types for a second. We've gone over some of the types here, but I kind of want to hit some of the other ones that we haven't hit yet. So we've talked about config. Here's the plugin interface, right? So the plugin itself holds an internal state, and that is sort of forward declared here, but not defined. It's defined by the plugin itself, right? So this audio types exists in the engine, right? So this is sort of you can think of this as the interface to the audio plugin. So we have an internal state that the plugin itself is responsible for standing up. We have the initialize, shutdown, update, typical with plugins. And then we have, the position query and set, orientation query and set, source gain query, source gain set. We also have the ability to modify pitch, which is exposed in the plugin, but not exposed in the front end yet. But that's another thing that I can pretty easily add. We have position query and set, looping query and set. Here are the chunk load and stream load functions from the back end. The unload function, source play on source, right? So basically, source play is saying just play on this given index, whatever is there, versus play a specific file on that source index. And then we have stop, pause, and resume. And that's the entire plugin interface, right? So it's not really that much more complex than the front end. Okay. So next thing we're going to take a look at is the OpenGL plugin main, or the plugin audio main, right? Which just declares a struct audio plugin, has plugin create, and it takes a pointer to an out plugin when it goes to create it, right? So this is the plugin's entry point. This is what the application looks for and calls to go ahead and create the plugin. So if we open plugin audio main C, this works just like the Vulkan plugin does, right? So this takes in a pointer here and assigns our function pointers, right? And then it says OpenGL plugin successful, OpenGL plugin creation successful, right? Just to let us know that that thing has worked, right? So all this does is set up all of our function pointers for our plugin. That's it. So that is loaded up in our testbed entry.c. So we had this renderer plugin create function or pointer function declaration up here. We now have a new one for audio. And then if we look a little bit further down, so this is where we're loading the testbed game library, right? And all of the application functions for that, assigning those function pointers, invoking the onload for the game code. This is our file watcher for that. Then when we go ahead and create the application, where we do the plugin loading is here. So we load the Vulkan renderer plugin, and this basically loads up the library Vulkan renderer, right? And then from that library loads plugin create, right? Then we go ahead and we call that plugin create. We follow this exact same pattern for the OpenGL plugin. So we say, okay, load a plugin called plugin audio OpenGL. From that library, load plugin create, the function pointer rather, and then execute that function pointer. And then say, you know, hey, if we fail to create that, false, right? So it's the same interface as what we did for the Vulkan plugin. It's just here, right? And that's really that's how the application stands up the plugin and gets it ready for use and tells the engine about it, right? Okay, so we have that. The next thing is to actually look at the plugin's implementation itself. This is actually the last piece of the puzzle, right? So we'll look at the header file first, which, if you'll notice, is just that plugin interface, right? There's nothing, I don't think there's anything else extra here, right? This is literally just all those function pointer definitions, right? So what we're going to do is we're actually just going to go to the C file, because there's nothing fancy here to see. So this is OAL plugin C. So this is the only file that actually has anything to do with OpenGL in it. And you'll notice there's a little bit of specialness going on here. Because of course, the way that OpenGL works on Mac and Linux is different from the way it works on Windows. On Windows, there's actually an SDK you have to actually download and install. Versus on Mac and Linux, it's a package that you install. So actually, if we look at the README, I think I put it in here. Yes, here we go. The audio, I forgot to put the Windows version in here, so I'll need to add that. So the audio plugin requires installation of OpenGL. So for Linux, use a package manager to install OpenGL if not already installed. So it would be sudo apt install OpenGL or sudo pacman s OpenGL for Arch, right? Mac OS, we install OpenAL Soft via Homebrew because that's what Homebrew has on it. So it's just brew install OpenAL Soft. And note that on M1 Max, this installs to a different location than USR, lib, include all that stuff, right? And so we actually updated the makefile to take that into account. So I'll show that towards the end. Like I said, the Windows version actually requires the download of an SDK, and of course the way that those things are laid out hierarchically. I don't know if that's a word. The way the files are laid out is different. So in Mac and Windows, or in Mac and in Linux, they are under a AL folder, and then you have AL and ALC.h. On Windows, they're in a separate structure, so you just have AL and ALC.h for includes, right? Kind of annoying, but that's some of the only platform code that we're going to see in here. All right, so we have the audio file plugin data. So this takes, this is the plugin data for a individual file, right? And so, I'm sorry, not a file, a source, right? And so all those sources can be looping, yes or no, right? And then a source either has a single buffer, in the case of sound effects, right, where we load the whole thing in one shot, or multiple buffers, in the case of we're streaming audio. And so we have OAL plugin music buffer count defined as 2. And so this technically is a buffer count of 2. And the reason we do that is as we're streaming the data, we queue up buffers on a source. So we say, okay, here's a first source that's loaded with data. Start playing that. I'm going to load up the second source and queue it after that when it's loaded, right? And then when that second source is playing, we're going to take out the first source, load it with the next bit of data, and put it back on the end, right? And we're just going to keep moving them to the end, right? And moving it down and moving it down and moving it down. And so we can just reuse 2 buffers to do that when we're streaming data. So that's essentially how that works. The audio plugin source, this is the internal data for the source, right? So this is something that the audio system doesn't know anything about. It only knows about a source ID as far as the emitter is concerned, but that's as far as it knows. So a source here is basically a ALC uint for the source ID. So like OpenGL, it gives you IDs for everything. So this is the ID of the internal source from OpenGL itself. Gain, which is effectively the volume, pitch, position, whether or not it's looping, and whether or not it's in use. We also have a worker thread for this source. So this is something I haven't brought up yet. So playing a sound is a blocking operation. And that's an important thing to keep in mind because if you were to play that on the main thread, nothing else could happen on the application until that sound is finished playing, which obviously we don't want. And so the way that this has to work is you have to play the sound on a different thread. And the way that I initially had this hooked up, I was using the job system to do it, but the job system is really not ideal for this because we'd just be using up a bunch of job threads for absolutely no reason. So we actually create raw K threads here and use them. We create 1 thread per source. So each source has its own thread that just kind of sits there and spins and runs the whole time. And if it's playing something cool, if it's not, then it just kind of waits a little bit and then goes again, right? We also have a data mutex, right? So everything from here down should be accessed and changed during a lock, right? And this is because we're multi-threaded, right? So we have the ability to change the file. We also have the ability to trigger a play and trigger an exit, like a shutdown, right? And these things need to happen from the main thread, right? But we don't want to be updating those from the main thread if the current thread is, or the worker thread is accessing it, right? So we need a mutex lock there. The audio plugin source, the source itself takes, the audio plugin state, rather, takes a copy of the plugin configuration. We have the device, the audio device that's given to us by OpenAL, the audio context, which is given to us by OpenAL, a pool of buffers to be used for all kinds of music and playback. So these are those individual buffers I was talking about. We'll have, in this case, 256 of those, right? But it's configurable, right? So if we wanted less of that to save a little bit of memory, we could do that. Here's the total number of buffers available. We have the listener position, listener forward, and listener up vectors. And then we have the array of sources themselves, again, configurable. And then an array to keep free available buffer IDs. And we may or may not wind up needing that, but for now I'm keeping track of it. Okay, so we've declared a couple of methods here, a few helper methods. So we have a check error, which is kind of like our VK check. So if we peek the definition on that, we just say we do AL get error, which is similar to GL get error. We say if it's not equal to no error, then we go ahead and we say, what's the string for this? And then put out an error message, right? And the string for that is given to us by the error string, right? This is another static method. And we have some basic errors here, and this just spits out a string representation of that, right? Nothing too complex. Source create. Source create is basically to create a source, right? Nothing too crazy there. So I think we'll get into that in a minute. Source destroy, pretty self-explanatory. Find free buffer. This basically just loops through that buffer list and finds one that's free and returns it, right? So there's that. So the next thing is this hack can actually go away. That's done. I'm going to come back to these stream methods because they won't make sense until I explain a couple of other things first. So I mentioned before that each one of these threads has a worker. Each one of the sources has a worker thread, right? So this is the parameters to start up that thread. So we just keep a pointer to the plugin and a pointer to the source that the thread belongs to, right? And so this is the entry point for that particular thread. So we go ahead and we get the typed params, which is just this guy. We grab the plugin, we grab the source plugin, pointer rather. We go ahead and we release the params right away because we no longer need it after this. We've extracted everything we need here. So when we create this and we spin off the thread, we immediately detach it. And because of that, the configuration would go out of scope if we didn't actually allocate dynamic memory for that. So we actually have to allocate dynamic memory for that and then free it in here. We'll see we'll see the other half of this in a minute. So we just say we're starting the source. Here is the loop for that thread, right? So until do break is set to true, we keep looping, right? Now, if for some reason our data mutex internal data is nothing, in other words, it's a null pointer. If that happens, then we break out immediately, and that can happen because something kills the thread. Like maybe we shut down the main application and it just killed the thread. Like we hit the close button or something, right? If we didn't do that, this would continue to run and try to lock the mutex, which might not exist anymore. So we have to check and make sure it's actually valid first. And if it's not valid, we kill the thread. Next, we do a mutex lock. And we check to say, hey, is a exit triggered? If so, go ahead and break. Did we trigger a play? If so, AL source play. That's to play a source, right? So we just pass the source ID. It plays whatever buffers are queued up. We'll see that here in a minute. And then we flip that flag back to false. Then we unlock, right? So any of these things, any of these operations here, we need to lock to actually do. So we lock, check those things, unlock. If we have a current source and the current source is type music stream, we perform an update on that, right? And so this is what determines what's playing, if we need to buffer any more data from the stream, and so forth. So if we are streaming, this is constantly checking to say, hey, do we need more data? Do we need more data? Do we need more data? And so that's what that's doing. And then we sleep for 2 milliseconds and do the whole thing again, right? And so that's just constantly running. Whenever that breaks, we just say, hey, we're shutting this down, and return 0 for success. So when we are doing this stream update, right, since we're talking about it, what the stream update does is right here, right? So first off, it makes sure that, we actually have pointers to the things we need. It gets the current source state. So it checks the source and say, hey, what's your current state? And if it's not playing for some reason, then it goes ahead and plays, right? It says stream update, play needed for source ID. This can sometimes happen, particularly if you've queued up buffers with really small amounts of data. It could technically finish playing those amounts of data before the next buffer is ready to go, right? And so you shouldn't ever make your buffer size too small for that reason, right? But if that happens for some reason, this will catch it and replay it, right? So the next thing is that we need to check for processed buffers that can be popped off, right? So processed buffer is a buffer of audio that's already been played by the source. And so once that once the buffer has already been played, it's considered processed. And so here we say, okay, what's the number of buffers we have processed? And then we loop through those and we unqueue those buffers, right? Because we don't need them on there anymore, right? So we unqueue them one at a time, right? So we get the buffer ID that's unqueued here. And then it says, okay, we're going to stream music data, right? And so the stream music data says, okay, grab the next bit of data from the file, unless we've reached the end of the file. If we reach the end of the file, this returns false. If that's the case, then we say, okay, well, this particular file is done streaming, right? So if we're set to loop, in other words, we should loop the music or loop the stream, then we say, okay, loop around. So we call the audio rewind. That's on the actual audio file itself. It's passed. So we reset that back to the beginning. And then we say done is equal to not stream music data, right? And so if we actually get data back after we've rewound it and say, okay, give me the next chunk of data, then done would be false in this case, right? And then we say, okay, well, if we're not set to loop or we're done playing or whatever, then we're done and return false, right? And then we don't actually keep looping this thing, right? If we're not done, right, then we go ahead and we queue the next buffer. So we say we're going to queue one buffer, and the buffer ID that we unqueued here is the same buffer that we're going to use, right? So that buffer ID, incidentally, is the same that we stream data into right here, right? So if we look at stream data, this isn't very complicated either. Again, we just make sure that we have plugin and audio. We call the audio file load samples. Now, this is the audio file itself, right? Which is a whole other thing we have to get into. So we say, hey, audio file that we've loaded up, how many samples do you have left, right? And if the size comes back as invalid ID, U64, then that means we have some sort of error, right? That's the way these have been programmed. And in that case, we say we have no data left. If the size equals 0, that means we're at the end of the file. We have no data left. Here we go ahead and we check the AL errors, right? Because AL errors, it's an error stack, but it's a stack size of 1, right? So we check this just to make sure that that stack is cleared out before we call the next thing. Next, we go ahead and we load the data in the buffer, right? So we say stream data is audio, so the audio file stream buffer data, right? So we call that, and that gets us our stream data. If we have stream data, Then we call it AL buffer data. This is like GL buffer data to like upload, when we upload vertex data or uniform data or whatever to the GPU. This is the equivalent for that for audio, right? So we call AL buffer data to the buffer that we're going to upload to. We pass in the audio format, the streamed data that we got from here, the size, right, of the data. So we got that up here, and then the sample rate, right? And then we check for an error again just to make sure it didn't bomb out or something, okay? If we did not get stream data, then we say, hey, we've got an error streaming the data, and in that case, check the logs for more info, right? We boot out. We say there's no more data. And we have ads. Got a little over a minute on ads, and then we'll be back. Got about 20 seconds on ads. Okay. So the last part of this streaming the data is that audio to total samples left that we had. That tells us how far we are through the file currently streaming it, right? So we just subtract size from that. So this basically just gets called again and again and again just to stream that data, and then that's called from the update, right? So as long as we're streaming data, it's just going to keep loading in that data, right? And that's basically how streaming works. That's the most complicated scenario that we have in here, right? So that is that. All right, so initialize basically sets up the sources, right? So if we have max sources less than 1 for some reason, we default to 8. If we have max buffers less than 20, it says defaulting to 20, but it's actually defaulting to 256. So let's change that to 256. Yeah, I guess that's fine. I don't think we need 256, but it's fine. So we load in the buffer count, free buffers. We create an array for that. This is all pretty self-explanatory stuff. What we're doing right here is we're getting the default device. So I do have a to-do here. There is an extension that's available, potentially, but it's an extension, to be able to pick a device. And so we might have the ability to actually pick a device later on, but for now I'm not going to support that. So just calling ALC open device with 0 just picks the default device, right? We go ahead and we get a context and set it current, just like OpenGL. So we configure the listener with some defaults. So we say the position is 0. The orientation is vector 3 forward, which is basically just z-axis forward, and then vector 3 up, which is this y-axis up, right? We just set those as defaults. There is something called velocity in here, which can be used to, for sounds that are kind of moving by fast or whatever. So that may be something I implement at some point, but for right now, I'm going to just zero that out, right? We go ahead and we create an array for our sources based on the max sources that we have. We set up those sources, we set up our buffers, right? So here's our create source that we have. I'll go into that in a second. Here's our buffers, which is just AL gen buffers. We have the buffer count here, and then the buffers array that we created here. And then we just check error, right? Then we also go through and we make sure that all of the buffers are marked as free. So basically what we're doing is we're taking all the buffer IDs and pushing them into the free buffers array. An important thing to note here is that we actually need to use the buffers array that we retrieved directly. So we can't always assume that the buffers start at ID 0 or 1. I saw this on Windows where it started at ID 9. 9. I don't know why it didn't start on 0 or 1. That would have made sense, but no, it started on 9. And so yeah, that's why I put this in here, right? So that's that. The shutdown basically just goes through, destroys the sources, closes the device, all that stuff. Plugin update doesn't actually do anything right now. That may change. I don't think so, but for right now, it doesn't really need to do anything. All the update logic is handled on the front end. So all of the position query and position set, all these query and set functions, all they do is they just set the property within the plugin state, right? So the position is just the listener position. So that's the sort of getter. This is the setter for that. The setter just calls a OpenAL function along with it, right? So we set this to cache it, right? So we can query it later. But then we say AL listener 3F position set to X, Y, and Z. Orientation query is the same thing. So we have the out forward and out up, right? Those are pulled directly from the state. The orientation set is the same thing, same concept, right? Source set defaults. So we set the gain default to 1, the pitch to 1, so that's 0 to 1. The position, we just set it to vector 0. And then looping, we set to false. So we just set the defaults on all the sources to start with. Then here's our source create. So there's not a lot to this either. We just create one source, check to make sure that it created successfully, set some defaults on it, create the mutex, and then start the worker thread, right? And so when we were talking about those params that we dynamically allocate, here are the thread params. We set the source in the plugin, call kthread create and detach, right? And that's it. Source destroy, we just say delete sources, one source to delete by the source ID, 0 the memory out, and then source ID is invalid ID. Find playing sources. I'm not 100% sure that we're going to need this anymore, but we might. So this basically just loops through each individual source and gets its state and says, hey, is it playing? And then jam it into this array. That's all there is to it. Clear buffer. All this does is basically say, okay, for this particular buffer, for this particular amount. So we loop through the amount, right? And we say for each individual buffer, right? We say if that buffer pointer, right, at index A is equal to the internal state buffers I, then we go ahead and push it onto the free buffers list and return, right? So that's all that's really doing. Find free buffer. This one's kind of important. So this basically loops through. First, it gets a free count. And then if the free count is 0, it attempts to free one, right? So it basically loops through each one. And it pauses each individual source loops through and then says, hey, how many buffers are on this resource that are processed? Can we grab one of them? Is there one that's processed that we can use? If there is, go ahead and do it, right? And that's this to be freed. And if the to be freed is greater than 0, then we unqueue that buffer and we have a free one, right? And so we clear that buffer and then we go ahead and play, right? Otherwise, we don't even need to do, I don't think we need to do this. I don't think we need to do that. Otherwise, we resume the pause sources. We have to pause all the sources and resume them, because otherwise you can get a false result on this guy, which is really annoying. And then we go ahead and we free the playing sources array at this point, right? So then we go ahead and check the free count again if we were able to find one. Then we're good. If we couldn't find one, then we say, hey, we don't have a buffer, a free one, right? This means too many things are being played at once, and we can't do it. Otherwise, we nab the first one off the top, right? So we just pop a buffer ID off the top, reduce the free count, right? And we check that again. We just say, hey, this is how many are left. And this is the ID that we're using, right? And then return that buffer ID. Otherwise, we return an invalid ID, meaning we couldn't find one. Gain, set, and query. These are all these source, query, and set methods. They're just setting all these individual properties, so there's not really anything of note there. We've already gone over this. Okay, so stream load. So this is the open of a music file, essentially, right? This one, essentially, let's see. We have the resource loader params, right? So we basically load the resource. We set the out file to the audio resource data. We set up the plugin data, so we allocate some space for that. We get some buffers to be used back to back, right? So we get 2 buffers straight away. In this case, it's going to be 2 buffers, right? So we find free buffers for those, and then check to make sure they're valid, right? We set the format. If the channel count is 2, we set to stereo 16 instead of mono. And then we set the plugin data is looping, right? So for music, automatically we kind of set default to true. Chunk load works a little bit differently. So it still loads up the audio resource from the resource loader, which we need to take a look at. We set up the plugin data again, once again. We get a single buffer this time instead of 2 buffers. And we basically just load the entire thing into it, right? So we set up the format, and then we say, okay, well, if the out file has something left, we call stream buffer data against the whole thing, right? And we load straight into that buffer straight away, and this file will hold onto that buffer as long as it's open. It will always use that same buffer because it's basically the whole file is being crammed into one buffer, right? We check for error conditions, and then unload the resource, and we're done. Close obviously just kind of undoes above, so we just clear the buffer, free the plugin data, and that's it, right? We close the resource. And then source play basically does a mutex lock on the source, says if we have a current, trigger play, and set end use to true, and then unlock, right? And then that loop just kind of picks that up. Play on source, that basically says, okay, well, if we're a sound effect, queue up the buffer that's within that sound file, and use that. Otherwise, if we're a stream audio type, we loop through the 2 buffers, stream music data into both of them, and then queue those buffers, right? And then down here we say, okay, current is the file, end use is true, and then we call AL source play, and it'll start playing those things, and then we unlock the mutex, right? Stop just calls AL source stop, and then detaches all buffers from it, right? And then calls rewind on the source. Source pause basically says if the state is playing, call AL source pause. Otherwise, don't do anything. And then resume is if it is paused, call AL source play, right? I don't know why that was commented. And that is the plugin. Not a crazy amount of stuff there, right? Last but not least, we have resource loaders, right? So we have an audio loader, a new audio loader that is loaded here. The audio loader is basically what contains the audio specific information. We are using 2 audio libraries here because I didn't feel like parsing these things manually. We support STB Vorbis and MP3 files, right? We have some small header-only libraries that are used for that. So we have mini MP3 and STB Vorbis to load those things. Much like images, it really doesn't make sense to write this stuff manually, right? It would have just taken way too long. So we store an MP3 decoder for MP3 types. That's just a static variable that's used across all of them. The audio file internal either takes a Vorbis or audio 3 MP3 info, right? We have a PCM, which is the pulse code modulation buffer. That's the digital version of waveform data, basically, right? Samples. And so we have the PCM buffer if we need it, which is size AL short, which is a short that's I16, and then PCM size, right? And so when we load samples, we say, hey, are we a Vorbis file? Call the Vorbis library to get the interleave samples, right? And then we return the samples times audio channels in that case. If we are a MP3 file, then we go ahead and we return the samples left because we don't have to do this for the MP3, right? The buffer data, again, each one of these basically says what kind of file are we? Are we a Vorbis file? Are we an MP3 file? And so if we're a Vorbis file, we just return the PCM directly. If we're a MP3 file, then we have to get the position of where we are in the array and return the internal buffer plus that position, right? So we just get a pointer to somewhere in there, right? Rewind basically is seek start for Vorbis files, and then we reset the total samples left counter. For MP3, it's just as simple as resetting the counter. And then audio load, and I'm going to kind of breeze through this really quickly. So we get a formatted audio string, right? Which builds sort of a path to the audio file itself, sets up the resource data, the type of it, right? And then if we're an OGG, right, a Vorbis file, then we basically open the file and process all of its info, right? We get the info from it. That's where we get the channel count, the sample rate, how many samples we have left. And then if we're a stream, we set up a buffer for that, a PCM buffer and PCM size. And the buffer length is basically the typed parameters chunk size times I16, right? If we are not streaming, we still need a buffer, but it can hold all the data. So we just get the length of the entire thing, set up the buffer, set up the PCM size. We read all of those samples into the buffer. And then we make sure that the length samples is a multiple of 4, even if we don't have that much data, because OpenGL will crash if you don't do that. Found out the hard way. And then we set the total samples left, right? If we're an MP3, it's a lot easier. So we just load the MP3. We get the info from that. From the info, we get the channels and the sample rate, and then the samples left, right? And then we just load all of that up into our out resource and return true. The unloader, basically if it's a Vorbis, we close the file. I do need to look into disposing of the MP3 data, right? If we had the internal PCM, we go ahead and refree that array, right? And then we obviously unload the resource, right? And then audio resource loader creates. When we register this, it's a resource type audio, so we have a new resource type. The custom type is nothing. Here's our function pointers, and then all of the assets go in a new sounds folder. So under assets, we now have sounds, right? And we have some different test objects here, right? So this woodland fantasy is the sound, the music that I was playing, the fire loop we have here, and the test sound that I was playing there, right? And that, ladies and gentlemen, is our audio plugin. That is all there is to it. So let me just clean real quick and build. And I'm going to run it one more time. I'm going to shut the music off again. And we'll run this one more time. Incidentally, you'll notice that the fire is playing right now, even though we haven't loaded a scene. That's because we don't have an emitter yet with moving capability, right? That's because we tied the moving of the emitter to that light that moves back and forth. Since that doesn't exist yet, it's at 0, 0, 0, and that's why we can hear it, right? When we load this up, notice it changes. Right? So, that is that. That is that wrapped up. Let's see. What was your first project about? What do you mean my first project? What do you mean by that? All right, so while I'm waiting on that answer, I'm just going to push these updates that I made. And refresh the pull request. Where is that? Here. All right, let me just refresh this guy. And we are going to squash and merge. And I'll leave all the commit messages in there. But we are going to merge that into main and delete the branch. So now all this stuff is merged and into main. And you guys now have access to the plugin system. Check out main, git pull. All right. So I realize I kind of hurried through some of that, but it's getting late and I need to wrap up the stream. And so I'm going to, I think for tonight, just because I'm kind of tired and I can't really hang around on another stream, I'm going to raid Ferret Software, who's a ferret rescue run by Pirate Software, who's another game dev streamer here on Twitch. And he basically runs a ferret rescue for ferrets that were used in medical testing. Some of them were rescued from abuse and neglect situations, and he gives them a nice home and a nice environment to live. And you may not know this, but taking care of ferrets is extremely expensive. And the ad revenue from this channel alone pays the bills for all of those ferrets, for their food, their medical care, and everything that they would need. And he's able to give them a really good life, and I think that's an awesome cause. And so that is why we are rating Pirate Software. So yeah, thank you guys all for coming here and being here and hanging out with me, and I really appreciate it. And I will see you guys in the next stream. See ya.